Good morning and welcome back to my channel. Today we are going to discuss on a radiation physics topic, X-ray production and properties. X-ray production and properties. Let us see the discovery of X-rays. X-rays were discovered by a German physicist named William Röntgen in the year November 8, 1895. While he was studying the cathode rays stream of electrons in a glass discharge tube, he observed that another type of radiation was produced perceptibly by the interaction of electrons with the glass walls of the tube that could be detected outside the tube. This radiation could penetrate opaque substances, produce fluorescence, blacken a photographic plate and ionize a gas. So when he was studying a cathode rays in a glass discharge tube, he suddenly observed that another type of radiation was also produced, which was detected outside the tube, and the peculiarity of this radiation was it can penetrate opaque substances, produce fluorescence, blacken a photographic plate, as well as it have a potential to ionize a gas. He named his discovery X-rays because X stands for an unknown factor. So which all are the properties of X-rays? It is usually asked for many exams and we have to know a general ideas of X-ray. X-rays are invisible. As we all know, radiation can't be seen. X-rays have no mass. X-rays travel at the speed of light in a vacuum. X-rays travel in straight line. They have a very short wavelength. They are unaffected by electric and magnetic field. They cannot be refracted. They cause ionization, adding or removing electrons in atoms and molecules. They are transmitted by pass through healthy body tissues. They affect photographic film in the same way as visible light, turning it black. They are absorbed or stopped by metal and bone. They cause photoelectric emission. They are produced. So X-rays are produced when a beam of high energy electrons strikes a target. So, a high energy electron strikes a target. It results in the production of X-rays, and these properties makes X-rays very useful for medical diagnosis as well as treatment. So, X-rays are used in the radiology department as well as in the radiation oncology department, which I was discussed in the previous slides or the previous topics. X-rays are used as a mode of beam in the X-ray unit for taking X-rays. Likewise, the X-ray beam is used in the CT scan for taking images of cross-section of the human body. Likewise, X-rays are used in the radiation oncology, as in the case of radiation therapy treatment, as radiation is used for the purpose of therapeutic or treatment purpose for treating cancer patient. Again, let us see the X-ray tube. X-rays are produced in the X-ray tube, which is located in the X-ray tube head. X-rays are generated when the electrons from the filament cross the tube and interact with the target. The main two components of the X-ray tube are the cathode and anode. So, which is the component of the X-ray tube? The component of the X-ray tube is a cathode as well as the anode. The cathode is the filament and anode is the target. Cathode. Let us see step by step cathode. Cathode is composed of tungsten filament. So which is the material formed of cathode means tungsten is the material. The answer for that question is tungsten is the cathode material and it is seen in the form of a filament which is centered in a focusing cup. So in the area of the cathode there is a focusing cup too, and the cathode is formed of a filament and the material used is tungsten. The electrons are produced by the filament. So the filament is producing the electron. As we have discussed in the properties of the X-rays, when a fast moving electrons hit the target, X-rays are produced. In the before slide I told you that cathode and the anode is a component of an X-ray tube and the cathode is the filament. So the electrons are produced from the filament. Electrons are produced from the filament which is focused to the anode. So anode is the target, and that when these electrons hit the anode target, the X-rays are produced. The focusing cup has a negative charge like the electron. As you all know that electron is a negative charge. So the focusing cup has a negative charge and this helps direct the electrons to the target, and you can see a cross-section view of the focusing cup as well as the filament tungsten. It will be seen like a circular filament. Next is the anode. Anode in the X-ray tube is composed of tungsten target embedded in a copper stem. So the material used as anode is also tungsten like that of cathode, and why we have chosen tungsten will be discussed in the upcoming slide. And this tungsten target is embedded in a copper stem. Why we are using copper? Okay. So when this electrons is coming and hitting this target, out of 100%, if we are taking 100%, only 1% of X-rays is formed and 99% is formed of heat. So in order to avoid this heat or take away this heat, we are embedding this tungsten in a copper stem. So why we are using copper stem means in order to take away this heat from the target, we are embedding it in a copper stem since the target should not get too much of hot, since if it receives too much of hot, there is a chance for cracking the target. Why tungsten is used as a target as well as the filament? The choice of the tungsten as a target material in X-ray tube is based on two criteria. It should have a high atomic number as well as a high melting point. So the atomic number of tungsten is 74 and it is good efficiency or good in X-ray production. The efficiency is depending on atomic number. So the tungsten is used as the target material and it is having a high melting point of 3370 degrees Celsius. So it can withstand too much of heat when the electron is bombarding. So these two are the main peculiarity for choosing tungsten as the target material, and tungsten can be recoiled as a filament. So tungsten is used as a choice for cathode. So what is meant by thermionic emission? When a high voltage is applied between the cathode as well as the anode, the electrons are emitted from the filament which is accelerated towards the anode and achieve high velocity before striking the target. So the filament is getting heated up to producing the electrons when a high voltage is applied between the cathode and the anode, and we are having a focusing cup in the area of cathode in order to focus this electron towards the target, and the electrons is moving from cathode towards the anode. Anode is the target material, and from there X-rays are produced. So let us see what is meant by line focus principles. So from previous slides we discussed that X-rays electrons are coming and hitting the target anode. So the area where the electron is hitting, that area is known as the focal spot. So the area struck by the electron is called the focal spot of X-ray emission, and it is heated instantly. So too much of heat the target is getting when each electron is coming and hitting. During X-ray production, a lot of heat is generated. If the target is too small, it will overheat and burn up. In order to get a small focal spot while maintaining an adequately large target, a line focus principle is used. From line focus principle, provide a wide focal spot without compromising the resolution. So the image, a good quality image can be acquired with a small focal spot. So we have to use a large target. Since we are using a small target, it will be heated up and it will be burned up. So we have to get a small focal spot. In spite of that, we have to use a large target. So we are angulating the target by line focus principle, and that angulating principle is known as line focus principle. Here you can see the figure. The width of a target struck by the electron is AB, but when seen from the usual beam, its apparent width is CB. Okay, given by CB equal to AB sin theta. The smaller the angle, the smaller the size of the apparent focal spot. So CB is the area from the apparent focal spot. From there the X-rays are coming and the image resolution will be good, as well as we are angulating in order to reduce the heat burned up by the target. So what is meant by Heal effect? X-rays are produced at various depths in the target. They suffer varying amount of attenuation in the target. So when the X-rays are producing, there itself the attenuation is happening. There is greater attenuation for X-rays coming from greater depth than those from near the surface of the target. The intensity of the X-ray beam decreases from cathode to the anode direction of the beam. This variation across the X-ray beam is called the Heal effect. The effect is highly seen in diagnostic tubes because of low X-ray energy and steep target angle. The problem can be minimized by using a compensating filter to provide differential across the beam in order to compensate for the Heal effect and improve the uniformity of the beam. So what is meant by attenuation? Attenuation is the reduction of the intensity of the X-ray beam. So the X-rays are produced at varying depth. So the X-rays are produced in the target. So from the anode side, but from there itself it is undergoing varying amount of attenuation. Greater attenuation for X-rays is coming from greater depth that close near to the surface of the target. So the intensity of the X-ray beam is decreases from cathode to the anode direction of the beam. In this figure you can see the Heal effect. Here you can see the anode angle of about 15 degree. It represents to the line focus principle. So the attenuation is next to that, you can see the self attenuation. The attenuation is happening inside the target itself. So the attenuation means reduction of the intensity of the X-ray beam. So the attenuation, when it is coming down, the loss of the X-ray intensity towards the anode side, and it is going up towards the cathode side. So the loss of X-ray intensity at the anode side is known as the heel effect. Production of X-rays. X-rays are produced when rapidly moving electrons that has been accelerated through a potential difference of order 1 kV to 1 MV strikes a target, metal target. So the metal target is tungsten. So from this figure you can see the filament. Filament is the cathode and it is a glass, evacuated glass tube, and here you can see the anode as the target. The filament will be always cathode and the target will be always anode, and both the material is formed of tungsten. The kV range is usually seen in the diagnostic radiology, and MV range of beam is seen in the radiotherapy department. Production of X-rays. X-rays from a hot element are accelerated onto a target anode. The source of electron is the cathode or negative electrode. The electrodes are stopped or decelerated by the anode or positive electrode. The electrons move between the cathode and the anode because there is a potential difference in charge between the electrodes. When the electrodes are suddenly decelerated on impact, some of the kinetic energy is converted into electromagnetic energy as X-rays. Less than 1% of the energy supplied in is converted into X radiation during this process, and the rest is converted into the internal energy of the target. It means when the electrons are hitting the target, only 1% of X-rays is produced, 99% is formed of heat. So here you can see heated filament emits electron by thermionic emission. So by means of thermionic emission, the filament is getting heated up and the electrons are ejected, and it is moving towards the cathode, and the X-rays are produced when high speed electrons hit the metal target, and this target is embedded on a copper rod for heat dissipation. Electrons are accelerated by a high voltage. Again, let us see the physics of X-ray production. Bremsstrahlung X-rays as well as characteristic X-rays are produced in the X-ray tube. Bremsstrahlung X-rays is otherwise known as breaking X-rays. So here you can see two figures. So just keep in mind these two figures. In one figure you can see a center nucleus and a fast electron is coming, attracted towards the nucleus. Then it is changing the direction and going to some distance. So when it is changing the direction, it is losing its energy, and this energy is released as X-rays. In the second figure, you can see the high energy electron is interacting with the K shell. Means this is the nucleus, the nearby shell is the K shell. When it is interacting with this electron, it is knocking out this electron. So X-rays have a potential for ionization. So it is knocking out this electron, and a vacancy will be filled here, and the electron from the next shell will be filling this vacancy with the release of the energy, or it may be the release of X-ray energy, and this process is known as characteristics X-ray. So kindly keep these two figures in mind. Let us move ahead to see more about this. Bremsstrahlung X-rays. When an incoming free electron gets close to the nucleus of the target atom. So tungsten is a target atom. It is having a nucleus as well as the K element shell. So when this electron from the filament is coming towards the anode, that means the target atom, the strong electric field of the nucleus will attract this electron, thus changing the direction and the speed of the electron. So once it gets attracted, but it will be changing its direction. When the electron is changing its direction, the electron will be losing energy, which will be emitted as an X-ray photon. The energy of this photon will depend upon the degree of interaction between nucleus and electron, that is passing distance. X-ray originating from this process are called Bremsstrahlung, German word naming breaking radiation. So the other name for Bremsstrahlung radiation is breaking radiation. The X-ray energy depends upon the interaction distance between the electron and the nucleus. It decreases as the distance increases. Since the electron may have one or more Bremsstrahlung interactions in the material, and an interaction may result in partial or complete loss of electron energy, the resulting Bremsstrahlung photon may have any energy up to the initial energy of the electron. Also, the direction of the emission of Bremsstrahlung photon will depend on the energy of the incident electron. As electron energy below about 100 keV, the X-rays are emitted more or less equally in all directions. As the kinetic energy of the electron increases, the direction of the X-ray emission increases forward. Therefore, transmission type targets are used in mega voltage X-ray tube accelerator. These mega voltage X-ray tubes are seen in the radiotherapy department in linear accelerator, in which the electron bombards the target on one side and the X-ray beam is obtained on the other side. In the low voltage X-ray tube, it is technically advantageous to obtain the X-ray beam on the same side of the target, that is at 90 degree with respect to the electron beam direction. So this is what about Bremsstrahlung radiation. Again, let's see about characteristics X-rays. When the energy of the electron incident on the target, so it is also incident on the target, exceeds the binding energy of the electron of the target atom, it is energetically possible for the collision interaction to eject the electron and ionize the atom. So the electron coming from the filament should be having that much energy to overcome the binding energy of the electron of the target material, and it will be interacting with the K shell electron, and it will be kicking out that electron from that K shell, and the K shell will be having two electrons. So ejected K shell electron you can see in the figure. So there is a vacancy formed in the K shell. In order to fill this vacancy, an outer shell orbit will be filling. Outer shell is the L shell, and an L shell electron will be filling this vacancy with the ejection of a radiation. That radiation is known as characteristics X-ray. So the unfilled shell is energetically unstable, and an outer shell electron with less binding energy will fill the vacancy. Binding energy means the binding energy of the K shell will be high compared with the other shell, since it is close to the nucleus. As this electron transits to the lower energy state, the excess energy can be released as a characteristic X-ray photon with an energy equal to the difference between the binding energy of the electron shell. With higher atomic number target and the transition involving inner shells such as K, L, M and N. Again, we will discuss about continuous X-ray spectrum. The Bremsstrahlung X-ray energies is ranging from 0 to the peak and back to 0, and this is referred to as a continuous X-ray spectra. The majority of the useful X-rays are in the continuous spectrum. The maximum energy will be equal to the kVp of the operation, and this is why it is called kVp. kVp means kilovolt peak. So in this diagram you can see a continuous spectra since it is increasing, reaching a peak, then coming back to 0. So which all are the factors which are affecting the X-ray emission? The output of an X-ray tube is described in 3 terms: quality, quantity as well as exposure. Quality means describe the penetrability of the X-ray beam. As we have studied, X-rays are having short wavelengths, so it have long penetrating power, and that's the main quality of the X-ray beam we are using in diagnostics as well as for therapeutic purpose, since X-ray is penetrating deep to the body tissue. With higher energy X-ray photons having a larger HVL. HVL means half value layer and higher quality. Quantity refers to the number of photons comprising the beam. So quantity means number of photons. Quality means the penetrating of the X-ray beam. And the exposure. Exposure is a unit of radiation. It is a measure of ionization per unit mass of air. So another factor which is affecting the X-ray beam quality and quantity. So it is clear, you can see an increase in current. So current is MAS. MAS means milliampere second tube current, where S is the exposure time. So current, when we are increasing the current and increase in the quantity. Quantity means number of photons, but no change in quality. Quality means no change in the penetration of the X-ray beam. So increase in the current will increases the quantity. Quantity means the number of photons, but the penetrating power there is no change. While we are increasing the kVp, kVp is the voltage, kilovolt peak, and increase in the quantity as well as in the quality. So quantity of photon is also increased. The penetrating of the photon is also increased. Then added filtration. In order to filter the beam, we are using filters. More about filters we will be discussing in the upcoming topics. So we will be using filters. So when we are increasing the filter, added filter means a decrease in the quantity and increase in the quality. So it will decrease the quantity of the photons. So we are mainly using filters in order to shape the X-ray beam by absorbing the low energy photons so that the skin dose can be reduced. For that we are using filters. So the quantity, it will be absorbing the low energy photon. So the quantity of the X-ray photon will be decreased but increase in the quality. Quality means the penetrating power. Then while increasing the atomic number, the target atomic number, increase in the quantity as well as quality. Then voltage ripple. It also the voltage ripple we are using, then it will be increase in the voltage ripple will result in decrease in quantity as well as quality. Number of photons will also be decreased the penetrating power will also be decreased. So with that, coming to the session of today's, thank you for your patience listening. Hope you all have enjoyed the session. If you have enjoyed, please don't forget to like as well as to subscribe my channel. Stay tuned for the next topic. Once again, thank you so much. Good morning and welcome back to my channel. Today we are discussing about intensifying screen. In the previous topic, we were discussing about radiographic film or the X-ray film, and we were gone through this term intensifying screen. So what's the purpose of using intensifying screen, or where these intensifying screens are seen? Why we are using is intensifying screen cassette. All those questions were there in front of us. So today we will be looking forward about intensifying screen, or this session is meant for knowing more about intensifying screen. At the end of the session of radiography film, I have said that the radiography which we were discussing now is about conventional modality, means the old modality. Now the radiography has advanced to digital radiography, means the X-ray films are digitalized. So as in the case of conventional modality, we were using radiographic film along with intensifying screen cassette. So today we are discussing on conventional modalities. These were the cassette we were used in the radiography department or the X-ray units. Different size of cassettes were available. 10-8, 15-12, 12-10, 17-14. Length into breadth it was mentioned or determined. So for extremities we will be using small size cassettes. For taking x-rays of foot as well as hand, we will be using small size cassette. So the front as well as the back portion of the cassette is there. The back, it will be lead foil to prevent the back scatter, means the back scatter radiation. In order to avoid that, we will be giving back side with lead foil, as well as the front portion of the cassette will be radiolucent material like aluminium or carbon fiber. Since the radiation should penetrate this cassette, then it is penetrating the radiography or exposing the X-ray film which is kept inside the cassette. So this is the image showing the intensifying screen. So from this image it is clear that the screens are seen inside the cassette. This is the cassette. The cassettes have been opened. So here you can see the intensifying screen. You can see the radiographic film. So the film in the front as well as the back portion, there are intensifying screens. So the film is kept a sandwich between the intensifying screen. So when we are eating a bread sandwich, the bread will be seen as the intensifying screen and the egg will be coming as the radiographic film. So this is the cross section of an intensifying screen and film with cassette. We have in the previous topic we have discussed about radiographic film, and the cross section of a film was determined in the previous topic. In this topic I am determining the intensifying screen and film as well as with cassette. Okay. So the plastic front is there, then a pressure pad, base, reflector. So the parts of an intensifying screen or the layers of the intensifying screen will be this reflective layer, reflector layer as well as the phosphor layer. Then the remaining, the lead backing, plastic bag, pressure bag, everything is coming for cassette, and the black color which is seen here is the radiographic film. So where the intensify, the phosphor layer is coming just above the radiographic film. Above there is a phosphor layer, below that black color also there is a blue color phosphor layer. So this is the cross section of an intensifying screen and film with cassette. So again you can clearly see this white color which is seen in the both sides are known as the intensifying screen. What is an intensifying screen? It is a part of cassette, and the purpose of the intensifying screen is to convert the X-ray energy into visible light spectrum. So the light photons will be exposing the radiography film. So the attenuated X-ray photons. Attenuation means the reduction of the intensity of the X-ray beam either by absorption or by scattering. So some of the photons will be scattered and some of the photons will be absorbed by the patient. And the absorbed photons, the attenuated X-ray photons, the absorbed photons will be falling on this cassette. Falling on this cassette means it will be falling on this intensifying screen, the top layer of the intensifying screen, and this intensifying screen will be converting these X-ray photons into visible light spectra or visible photons. These visible photons will be exposing the radiographic film and an image is acquired. This is what is happening in radio intensifying screen, which is used in the cassettes, in the conventional cassettes. So history of an intensifying screen, first developed by Thomas Edison in 1894. Initial screen used is calcium tungstate. So the material used is calcium tungstate. It is a form of a phosphor content. So let us see the advantages of the intensifying screen. So the advantage is that when we are using an intensifying screen cassette, it reduces the X-ray dose to the patient. So the patient dose is decreased. Short exposure time means reduce motion blur. Motion blur means the patient have a chance for movement. So we can acquire a short exposure time, and how this X-ray dose is reducing we will be discussing in the coming slides. So the principle behind an intensifying screen. Since it is a phosphor content, I have discussed that calcium tungsten is a phosphor content. So the emission of light by a substance. This you have studied in your plus 2. That means luminescence, phosphorescence and fluorescence will be having by the emission of light by a substance. So what is fluorescence? The light is emitted instantly, stops after a stimulus is removed, and it is conventional. While in phosphorescence, the emission of light is delayed beyond 10 raised to minus 8 seconds and continues to emit light afterglow, which is seen in digital radiography. So in conventional it is in fluorescence, and in digital radiography it is in phosphorescence, and we will be looking forward for digital radiography in the coming sessions. So this is what is happening. So when an X-ray photon is coming and falling on the intensifying screen, the light from the phosphor, that means the calcium tungsten is the content we are using in the intensifying screen, and the light from the phosphor is exposing the film. The same thing is happening, the process of luminescence in intensifying screen. Okay, it is clear from this image. Construction of an intensifying screen, it is having a protective coating. cellulose component which prevents the static elasticity and physical protection and surface cleaning. Then it is having a phosphor layer, then a titanium dioxide, then a base layer which is high grade cardboard or polyester plastic, which we were using radiographic film. We have discussed about base layer, same layer. Then we are having a reflective layer here that is formed of titanium dioxide. Then the phosphor layer. Phosphor layer is the main layer of intensified screen which is formed of calcium tungstate. Then this is the phosphor layer. The function of the layer is to convert the few absorbed X-ray photons into many light photons by photoelectric effect. So see, here you can clearly see how we are reducing the radiation dose. When 4 photons is coming and falling on the phosphor layer, double amount of light photons are emitted from the phosphor, and these light photons are interacting with the radiographic film and an image is acquired. So minimal amount of X-rays is required for giving out double of the light photons. Likewise, the patient dose can be reduced. So this is the photoelectric effect when the X-ray photons are interacting. So an atom will be having a nucleus. It will be having K shell KLMN. Yeah, and the electrons are revolving around in this K, L and M, and the nucleus is having protons and neutrons. So the K shell is having 2 electrons. This all physics you have about an atom you have studied in your +2. So when an incident photon is coming and interacting with the inner shell, binding energy, inner shell K shell electron, and it is kicking out that electron from there, and a vacancy is obtained, and the vacancy is filled by the next shell electron. So this ejected electron is known as a photoelectron, and when an electron from the nearby shell falls on the inner shell, it releases an energy as characteristics radiation. This is what is happening in intensifying screen 2. Desirable features of phosphor. So what all are the peculiarities of this phosphor layer means high X-ray absorption efficiency. It is having high X-ray absorption efficiency, high X-ray to light efficiency, emission spectra should be matched to film sensitivity, fast light emission, absence of afterglow, uniform light output, that is uniform dispersion in suspension medium. The main content is that the high X-ray to light efficiency should be there. The speed of the screen will depend on the thickness of the phosphor layer, size of the phosphor crystal, presence or absence of light absorption dye in the phosphor layer, phosphor conversion efficiency. Thank you so much for your patient listening. Hope you have understood the session. So simply the intensifying screen are seen inside the cassette, and the purpose of the intensifying screen is to convert the X-ray photons into light photons, and these light photons are exposing the radiographic film. While using an intensifying screen cassette is to reduce the patient dose, and it is very important in the field of radiology or in the field of radiation. If you have liked my channel, please don't forget to like this video as well as to subscribe, and see you soon with the next topic. Once again, thank you so much. Good morning and welcome back to my channel. Today we are going to discuss on radiographic films. So from the radiographic films itself, from the name itself, you understood that these films are related with radiation And these films are used in the radiology department. So where in the radiology department? Radiography films or the X-ray films. So from that you get the clue that these films are used in the X-ray units for recording the image. You might have seen X-ray films in your lifetime. These X-ray films are simply known as radiographic films. Films are also used in other modalities in the radiology department in CT scan, MRI, mammography, dental radiography. Mammography is related with the radiographic examination of the breast tissue. There also we are using films. So today we are going to discuss only on radiography films which are used in the X-ray units. So the X-ray film displays the radiographic image. Means if a patient is having a fall or if a patient have undergone an RTA. RTA means road traffic accident, and if the patient is suspecting for any fracture, then we will be immediately rushing the patient to the hospital for taking an X-ray, and the X-ray film will be recording that anatomy of that region of interest in order to determine whether the patient is having any problem, and if with respect to that readings of the X-ray film, the patient will be undergoing treatment. So the X-ray film helps us to record the information regarding that object or a tissue through which the X-rays are passing through the patient. So the mode of beam is from the term itself, it is understood that X-rays are used. And it helps in diagnosis. Diagnosis means finding out a disease and treatment of the patient's problem. And the energy of the X-ray beam is converted into light by intensifying screen. So how, where these intensifying screens are seen, which is converting these coming X-ray beams into light energy or light beam. So we have to know more about intensifying screen, where this intensifying screen are seen and how it is converting. All those things we will be discussing in the next topic. So the energy of the X-ray beam is converted into light by intensifying screen, and this light is exposing the film to record an image, and the image which is recorded on a radiographic film will be a permanent image. This is a brief structure of an X-ray film. The X-ray film consists of different layers: base layer, adhesive layer, emulsion layer. Other layers are there which will be seen in the next slide. So the emulsion layer is formed of silver halide crystal as well as by gelatin. And the base layer is formed of polyester. It can be of polyester, polythene or a thalapplate, and the most widely accepted is nowadays is polyester. This is the cross section of the X-ray film. These are the different layers of the X-ray film. It is having a supercoat layer, emulsion layer, adhesive layer, base layer. So the X-ray films are having, or the X-ray films are used are of double coated emulsion layer, and the single coated emulsion layers films are used in CT, MRI, mammography, etc. And X-ray films are always double coated emulsion layer films. Again, we will look forward for the introduction to the X-ray films. The first X-rays were recorded on a glass plate, and these were coated with emulsion on one side only. In the previous, it was coated on emulsion on one side, but nowadays the X-ray films are all double coated emulsion layers. And more about the layers we will be discussing on the upcoming slide. Cellulose nitrate base film was used in 1914 for recording X-rays. This film was single emulsion but was quite flammable. In 1924, the safety film made of cellulose triacetate replaced the cellulose nitrate base film. Now polyester film base are used. So nowadays the film having the base layer of polyester. Film base. Again we are going to discuss on different layers of the X-ray films. First we will be discussing on the film base. It is transparent supporting material. Function to provide support for emulsion layer. Polyester is used and its thickness is 0.007 in. So it forms simply the film base is providing is support to the emulsion layer and it is formed of polyester. Ideal features of base material: structural support for fragile emulsion, low light absorption, flexible, thick and strong, dimensional stability, non-flammable. Tinted blue film. Triacetate and polyester are clear and colorless. Blue tint is added to the X-ray film to produce a film that are easier to look at, causes less eye strain. Blue tint can be added to either to the base or to the emulsion. All present X-ray films are blue tint. Emulsion. Emulsion is an important layer of a radiographic film. So we will move on to the emulsion. Emulsion is the heart of the film. Since X-ray images are recorded on this layer, emulsion layer, the X-ray or the light from the intensifying screen interact with the emulsion and transfer information to the film. So the attenuated X-ray beams when falls on the intensifying screen, these X-ray photons are converted into light photons and these light photons will be interacting with the emulsion layer of the X-ray films and the image is recorded on the emulsion layer of the radiographic film and has two principal components. It can be silver halide as well as gelatin matrix. It consists of a homogeneous mixture of gelatin and silver halide crystal. In typical emulsion, 90 to 99% is AgBr, silver bromide, and about 1 to 10% is AgI. So, silver halide crystals can be silver chloride, silver bromide or silver iodide. So the radiography film deals with 90 to 99% of silver bromide and about 1 to 10% of silver iodide. The silver halide in an emulsion is in the form of small crystal. It will be appearing as crystal lattice. So here you can see an image of silver Ag plus, silver bromide Br minus and AgI. So likewise it will be appearing as a crystal lattice in a radiographic film. An imperfect crystal means perfect crystal has almost no photographic sensitivity. Several types of crystal defects are noted. You can see here a defects noted. Here you can see the crystal defects. A point defect consists of a silver ion that has moved out of its normal position in crystal lattice interstitial ions. You can see here. These are the defects which is seen in the crystal lattice. A dislocation is a line imperfection in the crystal. Causes strain in the wall structure. Iodine ion strains the crystal in this way. Chemical sensitization. Chemical sensitization of a crystal are produced by adding ethylene urine, a sulfur containing component to the emulsion which reacts with the silver halide to form silver sulfide. This silver sulfide is usually located on surface of the crystal and is referred as sensitivity speck. It is a sensitivity speck that traps the electron to begin the formation of the latent image centers. So we will be knowing more about sensitivity speck in the upcoming slide. So latent image is simply, you can see a sensitivity site. The sensitivity site is simply known as sensitivity speck. So latent image formation. Latent image is the first invisible image formed on the radiography film. Once we are exposing an X-ray film, an image will be acquired of that particular anatomy, and the invisible image which is formed on the radiography film is known as the latent image. So the relevant radiation interacts with the silver halide crystal. So this radiation, this light photon is interacting with the silver halide crystal as I discussed in the previous slide. Mainly the interaction which is happening there is a photoelectric interaction. The energy deposited into the film is in the same pattern as the subject that was exposed to radiation, and this invisible image is known as the latent image. A latent image on photographic or radiographic film is an invisible image produced by the exposure of the film to radiation, film to light, that means radiation. So the light means light is coming from the intensifying screen, that we will be discussing on the next topic. By chemical processing, by means of different chemical processing, we are making this latent image is made visible, called manifest image, means an image which can be visible. So this chemical processing, everything is happening in the dark room, and all those things related with processing we will be discussing in the upcoming topics. Formation of the latent image. So how a latent image is formed? Metallic silver is black, so it is this metallic silver that produces black areas on a developed film. Exposure to silver iodobromide grains to light photons emitted by screen X-ray exposure initiates the formation of atomic silver to form a visible pattern. So here you can see an image. The energy deposited from light photons ejects Br electrons. So in this image you can see a light photon is coming. Okay, and it is interacting with bromine. Okay, and when the light photon interacts with bromine, it will eject an electron, and the electron is trapped at the sensitivity spec, where it is trapped and temporarily fixed. As I said before, we are having some sensitivity spec. This electron will be rolling in this crystal, and at last it will be falling on the sensitivity spec. Since the electrons are having negative charge, it will be attracting the interstitial Ag positive ion. Okay, unlike charges attract. So the negative electron will be attracting this positive Ag ion, and the Ag ion and the electron combine to form neutral black Ag. So this in sensitivity spec, it will be formed of Ag, silver, metallic silver will be formed. Silver, the chemical formula is Ag. If greater than 6 to 10 Ag accumulates at spec, it becomes a latent image developer, that is, it is developable. Here you can see another diagram or a diagram showing the formation of latent image. So silver halide crystal you can see. Then there you can see a sensitivity spec. The crystals are seen Ag positive and Br minus. And the light photons is coming and interacting. In the first image you can see a light photon is coming and interacting with a bromine ion, and this will ejects. When a light photon interacts with bromine ion, it will be ejecting the electron, and this bromine will become neutral with the ejection of electron, and this electron will be more rotating or revolving in this crystal lattice, and at last it will be falling on this sensitivity spec. You can see in the second image, you can see the electron is seen in the sensitivity spec. So the charge of the electron is negative. So it will be attracting a positive Ag ion towards this sensitivity spec. And there the Ag positive will be interacting with this electron, and it will be become neutral, and it will be formed in the sensitivity spec. Metallic silver. Metallic silver, silver means Ag. The same process is happening with second light photon. Again interacting with next, in the down you can see the light photon interacting with again Br minus. Then the same thing is happening at the end. You can see the sensitivity spec is only formed of Ag. It means it is a latent image. Metallic silver forms the latent image. So steps in latent image formation. Step 1, the light photon interacts with silver halide crystal. The photon kicks out the bromine electron. In the step 2, the kick down electron romps the crystal until it is trapped in the sensitivity spec. In the step 3, the electrons attract the silver ion. The silver ion combined with electron to form metallic silver. This group of metallic silver forms a latent image. Again, in the previous slide, I have discussed that the emulsion layer is formed of silver halide along with gelatin. So, what is the purpose of gelatin? Gelatin is used as a suspending medium and binding agent for the silver halide particles. It is made from bone, hydrolysis of bone. Okay, the material used as gelatin. Why we use gelatin as a binder? The silver halide crystals get finely and evenly dispersed and remain suspended. It will be maintained in a crystal. It is optically transparent. Gelatin does not react chemically with the silver halide. It is porous, so the processing chemicals can penetrate through the silver halide crystal. Since we are processing by some solutions, this latent image should be processed to a visible image. As I said before, the latent image are the invisible image which are made visible by means of processing, and it is of some chemicals. All about processing we will be discussing in the upcoming topics. Next layer is the adhesive layer. It is otherwise known as the substratum layer. It keeps the emulsion layer and base adherent to each other during coating stage in processing. Provides uniform surface over which the emulsion can be coated uniformly, or it is not having an important role. Its role is only for coating stage. In order to make the base to coat with the emulsion layer, we are using an adhesive layer or the substratum layer. Then the supercoat layer, it provides a protection layer of gelatin, and it reduces the damages from scratches, pressure or contamination during storage, handling as well as at the time of processing, in order to give protection to the emulsion layer, we are using a supercoat layer, and the supercoat layer gives protection to the film. Thank you so much for your patient listening. Hope you have understood about X-ray films and the image formation in the X-ray film. All about manual processing, how this latent image can be made visible. It will be discussed in the upcoming topic. As well as these X-ray films are nowadays a conventional modality since it is advanced to computed radiography as well as digital radiography. Now the X-ray films are digitalized. So more about computed radiography as well as digital radiography we will be discussing in the upcoming topic. Hope you all enjoyed the session. Even if we are knowing more about recent modalities, we have to know something about conventional modalities too, since many of the departments are still following the conventional modalities in many hospitals. So you have to be aware of about conventional modalities too. So you all stay tuned for the next topic. Thank you so much. If you have liked my video, please don't forget to like as well as to subscribe my channel. Thank you so much once again. Thank you so much. Hi. This is N95 mask. Corona Christmas celebration missai. So ആ ക്രിസ്മസ് സെലിബ്രേഷൻ കുട്ടികളുടെ ഇടയിൽ മിസ്സാവാതിരിക്കാൻ വേണ്ടിയിട്ട് ഒരു വെർച്വൽ ക്രിസ്മസ് സെലിബ്രേഷൻ കാണാൻ പോവുകയാണ്. നമുക്ക് എങ്ങനെ വെർച്വലി ക്രിസ്മസ് സെലിബ്രേഷൻ നടത്താം. ഇതിനു മുന്നേ ഞങ്ങൾ ഓണം സെലിബ്രേറ്റ് ചെയ്തിരുന്നു. അത് ശരിയായിട്ട് പ്ലാൻ ചെയ്ത് അങ്ങനെയൊക്കെ സെലിബ്രേറ്റ് ചെയ്ത് ഇപ്പം നമ്മൾ സെലിബ്രേഷൻ നടത്താൻ പോകുന്നത് ത്രൂ സൂം വഴിയാണ് നമ്മൾ സെലിബ്രേഷൻ നടത്തുന്നത്. ജസ്റ്റ് some songs ഒക്കെ വെച്ച് മാത്രമാണ് ഇപ്രാവശ്യം നമ്മുടെ സെലിബ്രേഷൻ. Stay tuned, keep watching, and if you like my channel, please don't forget to like as well as to subscribe my channel. So the PT RAD Academics is not only meant for academics, it is also related with cultural activities. So today we are seeing a simple blog or a simple virtual Christmas celebration. So we are going to begin our celebration. So I am waiting. They will be joining shortly. So within a short period we will be starting our celebration. See, അങ്ങനെ സ്റ്റുഡൻസ് എല്ലാം ജോയിൻ ചെയ്യാണ്. ഫോർ സെലിബ്രേഷന് വേണ്ടി എല്ലാവരും ജോയിൻ ചെയ്യാണ്. പാട്ട് ഞങ്ങള് മിസ് ചെയ്യൊന്നുമില്ല. അതുല്യ പാടാൻ പോവുമല്ലോ, പിന്നെ എങ്ങനെ മിസ് ചെയ്യുന്നു? കുട്ടിക്കോ പാടാൻ? വീഡിയോ ഓണാക്കുക കേട്ടോ. വീഡിയോ ഒന്ന് ഓണാക്കിയിട്ട് പറ്റുമെങ്കിൽ ഒന്ന് അച്ഛനൊക്കെ ആയിട്ട് പാടിക്കോ. എല്ലാവരും ആന്റിമാരും എല്ലാം ഇൻക്ലൂഡ് ചെയ്തോ. ഇടയ്ക്കിടയ്ക്ക് സിഗ്നൽ വരുമ്പോ അതുല്യ വരാന്ന് പറയും, പിന്നെ അതുല്യനെ കാണുന്നില്ല. എല്ലാവരും കൂടെ ഞാനും കൂടാ. ഏത് പാട്ടാന്ന് പറയൂ, എന്നാ നമുക്ക് എല്ലാവർക്കും കൂടെ പാടാം. ഓക്കെ. അപ്പൊ യഹൂദിയയിലെ എല്ലാവർക്കും അറിയാലോ. പാടിക്കും. നിന്നില്ല, ഒരു സെക്കൻഡ്. പാടിക്കും. പാടിക്കും. രാജകുമാരിയോടൊത്തൊന്നൊരു തിങ്കൾ പാടി ഗ്ലോറിയ. Okay, okay. ഓക്കെ, ഇനി അടുത്തതായിട്ട് ഹിബ പാടുന്നതായിരിക്കും. ഓക്കെ ഓക്കെ. ഓക്കെ ഓക്കെ ഓക്കെ. അപ്പൊ പാടിക്കോ. വി വിഷ് യു എ മെറി ക്രിസ്മസ്, വിഷ് യു എ മെറി ക്രിസ്മസ്, വി വിഷ് യു എ മെറി ക്രിസ്മസ് ആൻഡ് എ ഹാപ്പി ന്യൂ ഇയർ. വിഷ് യു എ മെറി ക്രിസ്മസ്, we wish you a Merry Christmas, we wish you a Merry Christmas and a Happy New Year, Happy New Year, Happy New Year, Happy New Year, Happy New Year. അപ്പൊ എങ്ങനെയുണ്ടായിരുന്നു ഞങ്ങളുടെ ക്രിസ്മസ് സെലിബ്രേഷൻ? ഇതൊരു പ്ലാൻഡായ സെലിബ്രേഷനേ ആയിരുന്നില്ല. ഞങ്ങൾ പ്ലാൻ ചെയ്ത് അതിതകർപ്പൻ ഒരു ന്യൂ ഇയർ സെലിബ്രേഷനുമായിട്ട് തിരിച്ചു വരുന്നതായിരിക്കും. സോ സ്റ്റേ ട്യൂൺഡ്.